E2 mechanism. So if we have a compound like this, CH3, CH, H, and we have a leaving group here. We also have another option. It's like this. So there is a possibility that two different products will form. And of course, they will form. One product is by the deprotonation of this proton by a base, in presence of a base, of course, and another is due to the deprotonation of this proton. So you will get two different products. First product will be this, sorry, CH3, CH, double bond, CH, CH3. Okay, this is root A. So this is root A. This is root A. And what about root B? When the other proton will be deprotonated, they will get another product. Which will look like this. CH, double bond, CH2. So two different kind of alkene is formed. In the first case, the product will be a major product. Why? Because it is the most substituted alkene. What do I mean by most substituted alkene? If I look at the structure of the first product, it is like CH, CH, CH3. So one substitution here, one alkyl substitution here, another alkyl substitution here, methyl substitution in both the cases. In the next case, that is when the order will follow, or when the reaction will follow path B, then we will get something like this. CH, double bond, CH, H, and here we have only one substitution. Now, what is the significance of this substitution? Why is it so that this alkene is much more stable than this one, and why first one will form in a higher quantity compared to this one? I have already discussed it using the hyperconjugation. So let me take the two alkenes again. What is hyperconjugation? Let me tell that first. Hyperconjugation is something where it is kind of resonance where the double bond forms conjugation with the sigma bond of the carbon hydrogen. That means it will form sigma bond overlapping with this sigma bond, and it will come over here, this will come over there. So the resonating structure will look like this. So the H is now H plus, this is now double bond, and this is CH2 minus, and the other two proton will be like the same. Similarly, if I number these protons like proton 1, proton 2, and proton 3, this is a single bond, this bond is a single bond. That means it may rotate along itself. Okay, so next time after rotation of like 109 degree 28 minutes, what will happen? This H2 will come to this position, and this H1 will go down. And this is even possible in room temperature. So what will happen now? In the next structure, we will get something like this. Now this H2 is here, and H1 will come over here, H3 will come here. So now this H2 can again form another hyperconjugative structure with the double bond, which means for three different protons, three different hyperconjugative structures are possible. So for a single methyl group, three different hyperconjugations is possible. So now if we go to the previous image, we can see that here we have two methyl groups. That means here 1, 2, 3, 4, 5, 6. 6 hyperconjugative structures are possible. So this alkene is much more stabilized. As a result, this alkene will form. Now, why this alkene is formed? This is a product. Now let us go a little bit deep into the mechanism of the reaction. Okay. And if you compare it with this alkene, you can easily see that there is no possibility of so many hyperconjugative structures, because here only one CH, means one alkyl substituent is there. So of course, in this case, the number of in the first case, in case A, the number of hyperconjugative structure will be more. That's why it will be more. Now let us think about the mechanism of this reaction again. So let me draw again the two structures. So the first structure was like this: CH3, CH, H, CH pair, and single bond CH2, CH3. Yes, CH3. So now, in presence of base, first step will be the formation of a transition state. What is that transition state? So in presence of B minus, something like this will form. So this CH bond will now be a partial bond, because it's going to break, because the base is going to take the proton. This single bond will be like the same, but there will be a partial double bond character in this bond. There is no change because this proton is not participating, and this leaving group here is also going away. That's why a partial bond is formed. Now look at this structure carefully. Look at this intermediate structure carefully. Of course, this intermediate is going to break down to the corresponding product. We will get the product from here. Now look at this intermediate very carefully. You can see partial alkene character is developing, because a double bond is almost kind of developing in this molecule. So you can say that it has some alkene characteristics. It is not purely alkane anymore. It has some alkene characteristics. That's why this kind of forming double bond, which is not formed yet, so this developing double bond could be also stabilized by these two methyl groups. That means the transition state of this reaction can also be stabilized by the presence of these two methyl groups, which means the energy of the transition states will also be a little bit lower. How is it so? Let me draw the energy profile now. Okay. So let me draw the structure first. The starting material, that is CH3, CH, CH, here. Here we have a CH, and here we have another H. So this is the starting material. Now let us consider part A, which means the first product or the most stable product. CH3, CH double bond, CH, CH3. This is the most stable product. And the intermediate or the transition state, not the intermediate, but the transition state will look like this. Okay, this is path A, and there could be another path. Sorry. Another path will give you the second product, which is the minor product. And the transition state corresponding to that product will also have higher energy because it is less stabilized. That means CH, CH, PR, CH, 2, H. So this is one transition state, this is another transition state, and the direction of energy will increase in this way. So energy is increasing here in this direction. That means the energy of the transition state corresponding to product B or pathway B has higher energy, and the one which goes through pathway A has lower energy because the transition state also has some alkene characteristics, and it could be more stabilized in presence of the 2-methyl group or the 2-methyl substituent. Whereas in case of pathway B, the transition state is less stabilized because it doesn't have any methyl substituent attached to it. There is only one methyl substituent, of course, but that is not enough to stabilize the transition state compared to that of the first compound or the first product. So this is it about about E2 reactions. Now, as I'm comparing the stability of alkenes, now there must be something that we should discuss. Okay, let us take 3 different kind of alkenes. Let us take 3 different kind of alkenes. Let us take 1. This is alkene. This is another alkene. This is now as we know that a double bond of an alkene can be stabilized by the presence of its substituents, alkyl substituent, methyl substituent. It can be stabilized. Now here we can see that all these 3 alkenes have the same number of methyl substituent, isn't it? For the first one we have 2 methyl substituent. For the second one also we have 2 methyl substituent. For the third one, in this case also we have 2 methyl substituent. Now if we want to compare, or if we just go to the experimental result, we will find that this one, the first alkene, which is a propene, is highly stable. So the order of stability is like this. Will be stable, more stable than the trans alkene, and this trans one will of course be more stable than the 6. Now why is it so? Although all of these 3 alkene has 2 methyl groups or 2 methyl substituents, so these alkenes are substituted alkenes, and the number of substituents are also same, but the stabilities are different. So we can we use the comparable hyperconjugation structure in this case? Can we compare the stability of this compound using the hyperconjugation structure? Although we have to do that, but there are some other things that we have to include in this case. Now let us see, or let us draw the resonating structure or the hyperconjugations, the structures formed after the hyperconjugation, and compare those structures or the stability of those structures. Now, first of all, let us think about this propene or compound A. So for this, the hyperconjugation will happen. Suppose it is happening with this first methyl group. That means the other methyl group will remain as the same, and this CH2 now here is the H. Now this H is plus. Okay, here we have the double bond, and here we have the negative charge. So for these 3 protons, 1, 2, and 3, we will have 3 similar structures. And also for these 3 protons here, we will also have 3 similar structures. That means 6 similar structures. If you draw all the resonating structure, we will get 6 similar structures. Very good. Now what about this one? Let me draw the resonating structure for this one. Let me think about this methyl group first. We will get something like this. H and H plus, double bond here, single bond here, C, H, CH3, negative charge here. So the positive charge is here. Let me draw it more clearly. And the negative charge is here. Now we have a H here. Okay, now let us compare between these two. Before comparing, we should draw the corresponding resonating structure for the third one also. It will also be kind of similar. So here will be a positive charge. Here we have the other 2 protons. Double bond here, single bond here, C, negative charge, H, not H here, in this case we have CH3 here, and H. Okay, so these are the 3 resonance structure for the 3 corresponding alkenes. Now look very carefully towards this carbon ions. Now probably you already know that the stability of carbon ion also depends on the substituents around it. So in case where we have no substituent attached, that means a primary carbon ion is much more stable compared to secondary carbon ion, because the reason is very simple. The reason is that in this case, in the first case, we have only one alkyl group attached with the carbon ion, which means there is one inductive effect, okay, or one plus I effect, which means the electron is getting pushed towards this CH2, and this CH2 already bears a negative charge. So if there is an inductive effect which is pushing the electron towards that negative charge again, the system will be unstable. So the system can only be stabilized by taking away the electronic charge rather than pushing it. Now here we have only one plus I effect. So of course it will be a little bit unstable, but less unstable compared to this one, because in this case we have two alkyl groups. So 2 plus I effect will be acting on the same negative charge, which means this one will be less stable. So this one will be less stable. This carbon ion will be less stable compared to this one. The same will also happen for the third alkene. Here also we have 2 plus I effect active on the same carbon ion, which means the stability due to the plus I effect will be lesser. So the stability of this carbon ion will be lesser because of the presence of 2 plus I effect. And now we know that only in the first case the resonating structure is more stable. As a result, the compound is also stable. But what about the other two alkenes? Why the cis one is more stable? Why the trans one is more stable compared to the cis one? Here, some different factors is coming. That factor is called steric factor. So steric factor means it's about the size or the volume of the group. So when we have two methyl groups very near to each other, then there will be a steric factor. That means those two methyl groups will have a repulsive interaction with each other because they are trying to occupy the same space. So they will kind of have some kind of repulsion between one another. So that repulsion can overall decrease the stability of the system. That is what happening in case of cis-butene. So in case of cis-butene, the two methyl group which are very near to each other is kind of destabilizing the whole system because of their interaction. Whereas in case of trans-butene, we don't have that kind of interaction because the two methyl groups are just in the opposite side to each other. That means there is no such kind of steric interaction between. So there is no steric interactions. Okay. No steric interaction between the methyl groups. Very simply, we can say that that's why trans-butene is much more stable compared to that of cis-butene. So is it clear? Is it clear? If there is any question, you can ask me. Can you hear me?
Yes, sir.
Okay. So is it clear? Means if there is any question or things are clear. If it is not clear, I will repeat it. So please let me know if it is clear. So now Now let us go to E1 reaction or E1 mechanism. Just a moment. Have you heard the term E1CV? Anyone? E1CV? Have you ever heard this term E1CV? That is elimination single means elimination with the conjugate base. Have you ever heard this term? Anyone, please. Means I don't know your syllabus, so please, someone tell me that if you have that in your syllabus. You have E1, E2 reaction, isn't it?
Yes, sir.
Yes, sir. Okay. But E1CV was not there, isn't it? Not sure. If you're not sure, you can say that I'm not sure. Might be there. Okay. There is another thing about E2 reaction which I should mention is about the so when a E2 mechanism is happening, especially so suppose we have a reaction going on. Very simple example I'm giving. C H R can be any alkyl group and here again R1 R2 and the leading group. So in case of a SN2 mechanism, this is one configuration possible, and the other configuration, sorry, not configuration, but conformation is also possible. Like this. Now, R2, C, here. So this is R1, R2, and here is the leading group. Here is the proton. Now, these two conformations are possible. In the first case, this is called where the two groups, the leaving group and the proton, are in opposite to each other, is called anti. And this is called C, where the leaving group and the proton are on the same side. So this is called syn coplanar, and this is called anticoplanar. Okay, this is syn coplanar situation, and this is anticoplanar situation. Now, in case of E2 reaction, it is always favored. E2 reaction is always favored when the substituent, when the reactant is in antiform. That means a transition state which has configuration conformation like this, or anticoplanar conformation like this, will be much more favored. It is not that the other conformation will not go to form product, but it will take a form product, but will be less favored compared to this one. This transition state having anti-coplanar orientation of the leaving group and the proton is much more favored. So this one is much more favored. This is preferable. This transition state is preferable for E2 reaction. Okay, because of course the base has a bulky size, so it will come from a direction and it will take the proton. So if the leaving group which is going away is also on the same side, it will have some problem. Due to the steric problem, they will not they will prefer a side which is just opposite to each other. That's what it is. Now whatever I have told you about the preference of stereochemistry in case of E2 reaction, there are some exception about it. So suppose I have already told you that this product will be favored. This product will be favored, but this one is not favored because the transition state has higher energy. And the formation of this highly substituted alkene is also called, this is a rule actually, this rule of formation of highly substituted alkene is also called, do you know the name of that rule? Have you ever heard Jetset Rule? This is discovered by a Russian scientist whose probably the first name is Jetset. So according to his name, it is called Jetset Rule, that when there is an option that two different kind of alkene can form from the same substituent, then the one which has more substitution will be a major product. This is called Jetset Rule. Okay. So whatever we have discussed the reason of Jetset Rule, but the Jetset Rule is like that. Always the highly substituted alkene will form after an elimination reaction. Okay. This is a rule, but there are exceptions, and that exception has also a name, that is called Hofmann Rule. And why there is an exception? What actually happens in those cases where we get a Hofmann product? So now let us consider the size of the base. Okay, so here we didn't consider the size of the base. Now we have to consider the size of the base. So things will get a little bit complicated. I hope you understand up to Jetset Rule. Now we are going to discuss about another rule which is called Hofmann Rule, which is just the exception of Jetset Rule. So what about the size of the base? Now let us take an alkene, not an alkene, but a alkane which can undergo elimination reaction. This one. And the base that I am choosing is very bulky. So I will choose something like this, a bulky base. Okay, so what it will do now? Now also there are two preferences. It may take a proton from here, because here also we have one proton. So a proton can be taken from here. This will come over here, this will go. One option. The same thing will happen if I take a proton from this methyl. So I'm not considering it right now. Another option is that may take a proton from here. Now, as we know that path A is this path A is the path A, that will give you product which is CH3, CH2, C, CH2, CH3. Okay. Another pathway, the pathway B, which means when this one will come and this will go, this pathway will give you the product CH, CH3, CH3. So from the previous discussion, we already know that this is a stable alkene compared to this one. Fine. But what will happen in this case? The reaction also goes via the same transition state. That means it is a E2 reaction, of course. So there will be a partial formation of a double bond, and there will be a partial breaking of the CH bond, and also a partial breaking of the C-Br bond. That means that there will be alkene characteristic of the transition state, which may for this you may think that this stable alkene will be the more favored product and this will be the more major product, but not in this case. When the base has a very high volume, or it is very big in size, or it is taking a larger space, because if you check, if you are the base, if you yourself are the base, what which proton will you choose, this one or this one? If you are this bulky base, of course it will be difficult for you to get inside because you have a bulky methyl group nearby and also this portion nearby. So there will be a steric repulsion between you are the base, so between you and these groups around this proton. So you will not prefer that. You just want proton. Why shall you go to a place where there are steric hindrances are there? So you will always prefer a place or the site which is less sterically hindered. That means this proton, which is alone and it can be taken very easily, and there is nothing in between the base and the proton form any kind of steric hindrance. That's why this bulky base will take this proton, and if this proton is taken, of course the preferred product will be this one, not this one, and this is called Hofmann rule. So in first case, where the base is not a very large base, a more stable alkene will form because the transition state, which also has the alkene characteristics, will be favored, and that the rule which predict the formation of that highly substituted alkene is called the Jetset rule, and the rule which states that when the base is very bulky inside, a different alkene can also form, which is less substituted, but the transition state is favored because there are less steric hindrance between the base and the other part of the alkane. So that rule is called Hofmann rule, and the corresponding product is called Hofmann product, and this product is called Jetset product. Okay, so the product which is formed following uh, Jetset rule is called Jetset product. This is Jetset product. This is Jetset product. This one is Jetset product. This is a stable atom. And this one is Hofmann product. So I have written here one extra F in spelling of Hofmann. There is only one F. Sorry. So Hofmann product. This is Hofmann product. And this is Jetset product. Very simple. Okay, so